So now it's my pleasure to introduce the second speaker of this session, Dave Wecker from Microsoft. So David will be talking about the simulation and compilation of quantum algorithms. And Dave, you have a tremendous record of innovation behind you. So it's too much to mention all of it. Dave joined Microsoft in 1995, and then he helped create the Blender, which is a digital video post-processing facility. Later, you became architect for a number of PCs, including the handheld PC, the auto PC, and the pocket PC. After moving to intelligent interface technology, you built a neural network-based speech recognition system. For the mobile device division, he implemented a secure DRM on ebooks and pocket PCs. And Dave also created and was director of the e-periodicals before you became architect for emerging technologies, where you started to work on big data and also quantum computing, which is the subject of your presentation today. So David has over 20 patents for Microsoft and 9 SHIP IT awards, and we are very happy that you're here today, and we look forward to your presentation. Thank you.
So what you can tell is I can't hold a job. Could we have my slides? Thank you. So I'm going to build on this morning's keynote. I promise I won't use any jargon that I don't explain. And probably the best thing I could do is start with the funky acronyms at the title of the talk. The vertical bar and the right bracket are a mathematical symbol from Dirac notation known as a ket vector. All it is a column vector of complex numbers. The U is a matrix that's multiplying the vector, and in this case, complex and unitary, and the I is just a scalar. So an operation, a quantum operation, is a unitary matrix times a state vector. The vector is all your data. Your program is basically a string of these U's that are applied once after another, and it's just a matrix vector multiply. You now know quantum computing. Seriously, that's it. And we're going to show how this gets applied through the entire system. The entire simulator is actually called Language Integrated Quantum Operations, and hence we get an acronym that looks a little bit like the word liquid. And the second one's a little easier because it's just son of liquid, and we're going to explain what that one is as well. So let's start with some motivation. Why do we want to use quantum computing for anything? Well, our current estimates are from 1 to 200 qubits. Yes, I'll define qubits in a little bit. Are all that's needed to design a catalyst to do efficient fertilizer production. Why do I care about fertilizer? 5% of the natural gas in the world every year is used to make fertilizer. 3% of the total energy output is used for this process. It's a process you heard about this morning, actually from Matthias Treuer, if you were in the post-Moore's law session. And we know we can do better because plants do this by anaerobic bacteria in their roots that are doing this at atmospheric pressure and temperature with very low energy. And we're going to talk about this a little bit more as we get into the applications. Carbon capture. We're going to double the price of energy over the next 20 years just by trying to scrub as much carbon as possible from the point sources. If instead we could pull it out of the atmosphere, we could get rid of all of that increase. Problem is, we don't know how to do it. Again, we know that plants do. And if we could analyze the mechanism, again, about 1 to 200 qubits are our best estimates. I'm going to make some basis for these estimates in a little bit. We could solve global warming. It was also mentioned in the earlier session about doing room temperature superconductors. We lose a lot of energy in transmission lines. We have all sorts of inefficiency in motors. This is an area we can do a lot of good if we can actually model the materials. And then machine learning. This is going to take a little bit more in the way of qubits, but there's a wide area, especially in the areas of big data, where we know there are algorithms in quantum that are interesting. Should also mention a lot of the work we've done in quantum has fed back to classical. We've come up with different ways of thinking of the problem. This is back to building together the small ideas. And we found better ways to do, for instance, machine learning objective functions. Also, if you just take a look at supercomputer use, 35% are areas that would actually run better from what we can estimate on quantum computers. If we add in the lattice QCD, we're up over 50% of today's supercomputer usage. So there's a lot of areas that look interesting and look applicable if we can make this work. Should introduce the team. The upper picture is the group in Redmond. The bottom picture is the group in Santa Barbara. And then we have a set of labs that work with us all over the world, building materials, devices, control structures, all the things necessary to actually build a quantum computer. One of the things that Microsoft excels at is building systems. So we're not just trying to build qubits, we're trying to build the entire machine end to end, and this basically builds everything from the bottom through the top. So let's define some of our terms. A bit is 0 or 1, we all know that. And again, in the earlier session, a qubit is a vector that is some part 0, some part 1, and the alpha and the beta here are complex values. When we do a gate in classical computing, we have an input, we have an output, and a function that we perform. It's pretty much the same for quantum computing. As I said at the very beginning, it's a matrix. We do a matrix multiply of that alpha beta, and with the matrix there, we flipped it to beta alpha, so we did a NOT gate. The difference is we passed all combinations of alpha beta through this, and it'll flip the meanings of all of them at once, not just one bit. We describe our gates classically as a truth table. Here's an XOR gate. Quantumly, it's still a unitary matrix, and this is the XOR gate, a controlled NOT gate. If you think about it logically, that's exactly what an XOR is. But again, the two lines that come in are these complex vectors, and now we're combining all of that information, not just 2 bits. Classically, we run our machines forward. We do a gate, we go to the next gate, we go to the next gate. Quantumly, it's a matrix. You can go backwards through the matrix. And basically, everything you're doing in the unitary side or the quantum side is going to be runnable forward and backwards. Here's where we start getting into trouble. Classically, copying is really easy. We make temporary variables all the time. We do what-if calculations. We throw them away. It's impossible to make an independent copy. Once you start playing with the data, everybody's entangled with each other, and you touch one piece, if it's ever touched something else, you're touching all the pieces it's ever touched. This is hard. This makes programming really difficult and hard to figure out how to build these new algorithms. Noise, we all know about adding parity bits or Hamming bits. We know how to do error correction classically. The same thing's possible quantumly, but it's very hard. This is a major area of research. There's a lot of work going on, but this is why you need so many physical qubits to make a good logical qubit that's going to survive the noise. Storage. If you have n bits, you can hold one number, 0, 2 to the n minus 1. However, quantumly, n qubits holds 2 to the n values. This is where we now get this massive storage in a very few number of qubits. Input-output classically is linear. You got to load the data from somewhere, you process it, and then you got to store it somewhere. No better quantumly. In fact, it's worse. The output is statistical. You run it through, you get an output, and if the output was somewhere, a little above 50%, you may have to run it a lot of times to know that's where it really was, because all you're going to get back is a statistical sampling of what the output was. Back to the good news, the computation normally in an n-bit ALU, we do one operation, say on 2 values. Quantumly, we do an n-qubit ALU does 2 to the n operations at once. So we get massive parallelism on massive amounts of data, but it's just as hard to put the data in and really hard to get the data out. What this says is you really want to define the problems that match this well. It also tells you this doesn't replace classical computing. This is something that is a coprocessor, like a GPU. It does some things really well, and that's what you want to focus on. There are a lot of technologies. You can build qubits out of anything that has at least 2 quantum states. The ones on the left tend to be optical and room temperature and are much slower and bigger, but they're very easy to do in a lab comparatively. The ones on the right use semiconductor technologies, but very, very cold. About 100 times colder than outer space is where they have to run, so there's low enough noise that the qubits actually survive. Microsoft is focused in the bottom right corner, topological quantum computing. Now, this isn't a talk on that today, but the idea here is you get a really big benefit if you can build these very specialized qubits. They will last natively, the physical qubit, on the order of a minute. The gate speed's nanoseconds pretty much for everybody, but because they last so long and they're so immune to noise, the error correction cost is tiny. So for 10 physical qubits, I get a logical qubit. In the case of almost all the other technologies, I need anywhere from 1,000 to 10,000 qubits to get one logical qubit. So it's very hard to make these. No one has ever made one of these qubits yet, I should mention. We're trying. But if we do, it means we can get scale up very quickly to quantum computers that do actual real-world problems. So I'm here to talk about the simulator. And for the next few slides, I'm going to leave this website up. We have just released it a week and a half ago to the world. It's free. You can program a quantum computer this way. You can run algorithms. It does Shor's algorithm. It does quantum chemistry. And we'll give you more detail later. But the website is up on GitHub. You can go there and grab the whole thing, and we'll give you the details about it at the end of the talk. The simulator itself had to be a high enough level language to easily implement large quantum algorithms. We've done some very large ones, you'll see. Allow as large a simulation as possible on a classical machine. This means being really smart about the linear algebra that you have to do, that matrix vector multiply that's at the core of everything. Support abstraction visualization. So this lets you do various granularity levels of looking at the circuitry you're building or the algorithm you're building and printing it out, getting pretty renderings of it. Implement an extensible platform. So you can define your own quantum gates, your own operations, and put them into the system. It's also a compiler. It does multi-level analysis of circuits, allows many types of optimization, so we get extremely high throughput through these quantum algorithms. We do circuit rewriting for specific needs. For instance, some qubit technologies don't have some gates. You have to rewrite with equivalent gates. You have to handle noise. You have to do all sorts of things because of the technology you're working in. And then we want to compile into real target architectures, and that's at the end we'll talk about SOLID. That's its job, is compiling and running real quantum hardware. So we start with a language. In our case, the language is Fsharp. It's a functional programming language. I just happen to be from the school that we really like functional programming. It makes doing asynchronous code, makes doing parallel code, distributed code, all sorts of things easy. By the time you compile it, it's usually right. And I'll get off my soapbox at this point, but if you haven't looked at functional programming in general and Fsharp in specific, you might want to. It also has a scripting interface, just like Python, so you can run this in script mode without having to compile. And the simulator itself is really just a set of libraries, so you can link it to any high-level language that runs on a Windows platform. Everything gets compiled into gates. So these are the unitary operators we're talking about, and these gates are just functions. The functions are sent down to execute on one of three simulators. There's a universal simulator. This will do any quantum algorithm up to about 30 qubits in 32 gigabytes of memory. You want to do 31 qubits? Then you need 64 gigabytes of memory. Every qubit you add doubles your memory. So remember at the very beginning that matrix multiply, the vector, if it was 45 qubits, would be a petabyte of main memory. And the matrix is of equivalent size or bigger. So you run out of gas very quickly on a classical machine and how big a quantum computer you can simulate. As I said, real-world problems start in the 1 to 200 qubit range, and you're not going to get there anytime soon. There's a stabilizer simulator. This is a simulator that does a subset of quantum operations, but these are a subset that are easy and efficient to do on a classical machine. You can do tens of thousands of qubits this way, but you can't do a general algorithm, so what's the point? Well, it turns out all the error correction codes fit inside a stabilizer model. So you can do all the error correction research and do tens of thousands of qubits and figure out what would work for fixing the noise. There's also a Hamiltonian simulator. He's the moral equivalent of the universal. Do everything the universal does, but 10 times slower. Why would you want a simulator 10 times slower? Because it will actually apply gates for periods of time, which lets you actually simulate quantum systems, quantum chemistry, quantum materials, this sort of thing. All of these simulators run on one of three runtimes. There's a client runtime. This runs on your desktop or your laptop. There's the service runtime, which actually will run across an Ethernet to any number of Windows machines as a service. So you can tie together all the machines in your office or your lab and use them for simulations. And there's the cloud version that runs on HPC and Windows Azure. But there's a whole different way to do this. One of the nice things, again, about this language is after it compiles the code, you can ask for the abstract syntax tree back. So once you have a representation of all of these gates, all of these functions, you can build a circuit that's now data, and you can optimize it. You can do quantum error correction, rewrite it. You can do rewrites of those gates that are missing and put in other pieces. You can do noise modeling. And all of that can be fed back into the simulators again. So you have multiple ways of manipulating and working with the data. You can also export the data. It's linear algebra. So if you export it as linear algebra, you can send it to a supercomputing backend and have it do the linear algebra, which it's really good at, or send it to quantum hardware and actually run laboratory equipment. And finally, there's rendering. I didn't think this was going to be very important. It turns out this is what my researchers love more than anything else, is being able to do publication quality images for their papers and not have to draw them, let the system draw it for them. If you're interested, there's a paper up on the archive. This is also referred to on the website of the architecture of the system and how we built it. I'll give a reference also at the end of where all the archive papers are. Let's do the quantum hello world and show what it looks like in the simulator. So I'm going to define a function. This is a function called EPR. He takes a list of qubits, and it's going to do two functions. He's going to apply a Hadamard gate. So our qubit's going to start pointing at due north. We said it could be somewhere between 0 and 1, and we're going to flip them onto the equator. That's what the Hadamard does. The control knot will take the first two qubits in the list and entangle them. So now the two of them are, again, copied, but they're not independent copies. If I do anything to one, it happens to the other, and vice versa. So that's one line, and what it made was the diagram you see on the right. That was automatically generated. For this talk, we don't have a lot of time, so I'm just going to show you what the code looks like, and then the circuit it generates. So there's a bunch of gates. There's some measurement functions. Those are the M's. And then the lines became double lines, which are classical bits now once they're measured. Those are used to control other gates. And what this circuit does is take one qubit, the one on top, and transport it to the third qubit at the end. What's interesting is once they've been entangled, you can separate them as length of the universe apart. And supposedly, if you change or put the value into the first qubit, that third qubit will instantly get the new value. Wait a minute, what about relativity? Don't forget the classical measurements. You can't actually get the data back out. You can't get the information until you've done a classical channel across the universe to send those two bits. So you can send this extremely high-resolution floating point vector from one part of the universe to the other instantly, but you can't use it until you get the classical bits there no faster than the speed of light. So this is what teleport is in the quantum world, and this is the hello world circuit. And as I said, this is simple graphics. This is in the browser in SVG graphics, but you can also ask for LaTeX and get pretty pictures of anything out that you can get in the browser. Show you just one more circuit like this. This just shows you how a few set of lines can make a fairly complex circuit. We're going to call this one entangle. He takes a list of qubits. He's going to flip that first qubit down again, and then entangle it, C-knot it with everybody else in the list. So we're going to walk through the tail of the list and just C-knot everybody together, and then we're going to map a measurement on all of them. This is the circuit you get, depending on how long the list is you put in. And when you run it, the measurements are over on the right. You'll notice you get all zeros or all ones. It's random whether you get a 0 or 1, because the qubit's sitting on the equator, and when you measure it, it could go to 0, could go to 1. But once you've measured one of them, they all had better measure the same, because they're all entangled together. Again, no independent copies. The actual C-knot gate we're using for entanglement looks like this. The user can override any gate, can build their own. I'm assuming that's not me. Okay. Well, I'm just going to keep talking. So all the gates in the system are really just data structures with matrices. There's a line at the bottom. Do we have a loose connection? Pull it.
Yeah, just pull it back in.
No. Voila. Isn't modern technology wonderful? You'll also see a drawing line at the bottom. You actually have a language you can write drawings in, so you can actually make your own gates, make them look the way you want. I'm going to speed up a little bit because we lost a little bit of time there. But there's an extensive module for doing quantum error correction. You have to rewrite the circuits to go from physical qubits to logical qubits. The system does it automatically. We'll run it for you, analyze it for you. And so, for example, if we take a single qubit and want to expand it out in something called a SC15 code, this is what it looks like. The bottom 7 qubits are the physical qubits that makes up the logical qubit. The top 6 qubits are the error correction. They're measuring the information, figuring out what to do, flipping any errors that happen, and setting everything back. So if we take our teleport guy and pass it through the SC7 module, it now looks like this, and 3 qubits goes to 27 qubits. This is, like I said, you grow very quickly from physical qubits to logical qubits. We can also do very advanced noise modeling. In this case, we have a simple circuit where we're just sitting there with idle gates, waiting for time to go by. And we can watch the qubits getting worse and worse, and then there's a decoherence event. And qubit goes to 0, the second qubit goes to 0. Now we have a 100% probability of measuring a 0, 0, and nothing else at the end. So we can do all sorts of types of model, and it's user definable what the noise model looks like and how it works. This is actually applying the noise model to that teleport circuit and showing that we actually get the thresholds that were predicted a decade ago of what you should see when you get noise with teleport. So everybody's heard of Shor's algorithm. Let's use quantum computers for cryptography. I'm not going to go into it in great detail, but here's an example that shows you the RSA 2048 challenge, where we think classical computers would be to actually break it. You notice the billion years at the top. And then even a 1 megahertz quantum computer is about a day, a little over, or 100 seconds for a gigahertz. Everybody who publishes Shor's algorithm factors the number 15. That's about as big as anyone gets. This is a high-level view of that circuit. There's 8,200 gates in it, but we've asked for a higher-level view. With liquid, we've actually simulated factoring a 14-bit number. 8193 was 14 million gates, and it took 30 days on my desktop. Didn't need a supercomputer or anything else to do it. And the kit does come with Shor, and you can sit there and factor numbers with it. Here's just an example of what the code looks like to generate items in a modular adder for Shor's algorithm. And what's nice is you notice in the code there's a call to QFT, which is a quantum Fourier transform. That's just another set of code. This is now a modular adder that's called at higher levels, which is called by the modular multiplier, which is called by the modular exponentiation unit. So you can build libraries up of more and more abstraction and higher gate counts, and the user then just sees very high-level functions to work in. This is the first 3 versions of the simulator. The one at the bottom is the current one. You'll notice a 13-bit number to factor initially would have taken 3 years, then 4 months, and now 4 days. That the last triangle at the end is the 30 days for the 14-bit number. So you see we scale pretty well. We use all the cores we can. The problem is we can't run this distributed. We have to run this on a single shared memory machine with lots of threads because everything has to talk to everything all the time. That's part of the problem. But we can be more efficient than you might think. What we want to do is this matrix vector multiply. And we run out of simulation address space and physical memory very quickly. So if we look at the state vector, the guy on the right, we can break it up into pieces because if things haven't been entangled yet, they're very simple to define. Each qubit really only takes one set of 2 complex numbers. When we entangle them, they take more and more and more space. So we actually keep the state vector in pieces until you pull them together, and as you measure, we take them apart, and we give back memory as much as we can. On the operator side, it's usually very sparse. That's the good news, but a large amount of bookkeeping and overhead to manipulate it. But we can do better. What we're really doing is taking these little gates, like a CNOT touches 2 qubits, but you may have 100 qubits, or in this case, say 30 qubits that you're simulating. So what you really want to do is take that gate and tensor product it with identity matrix of the right size and then multiply it by the state vector, provided all the qubits are in the right order so you're able to do this. However, when you do that, the resulting matrix has bits all over the place, and everything has to talk to everything. If we could flip this, put the identity matrices first and then the gate, you get a block diagonal matrix. Everything becomes distributed, parallel, easy to do. So that's what you want to do. You want copies of this guy down the diagonal, and then I can just put them off on threads independently. But it means the qubits have to be in the right order, and I have to flip this Kronecker product. Well, there's some problems here. You have to do this permutation, which is very expensive, and then the Kronecker product isn't commutative. So you can't just flip them. However, there's always a permutation that lets you make believe. It lets you permute it before and after, and then you can flip it. So we just do the one permutation and keep track of it throughout all the computations. When you actually ask for a value, we unpermute the chain of permutations. So by doing this, we are always multiplying out a block diagonal matrix. We're extremely efficient. We figure out when it pays to change the order of the state, when it doesn't, and so we do as efficient a set of linear algebra operations as we can. We actually wrote our own sparse linear algebra package just for this system that's optimized for quantum operations. So people say, great, we'll just take classical algorithms, throw them on the quantum computer. Doesn't always work that well. In fact, it usually doesn't. Let's take the Google matrix for PageRank. We know how to convert it to a Hamiltonian. Once it's a Hamiltonian, we know how to simulate it. We turn it into a unitary. And now we evolve from a starting state, just like you would for PageRank normally. And you perform an adiabatic evolution. This basically says we're very careful about staying in the ground state, the lowest energy state, as we go through the system. And we get an output. Great, PageRank would work. So we'll do a synthetic web graph, just do 8 qubits, which is 256 pages, and sure enough, the classical PageRank and the quantum PageRank agree with each other. Great, we can do PageRank. Let's do the web. Well, there's a problem. First, you have to load the whole web into the quantum computer. Okay, it's no worse than classical, it's linear. Then you have to process the data. That's exponentially faster. That's great. We get that done before you blink. Now you get to read out one number. And that destroys the entire system when you read it. You got the page you landed on this time. You want an answer? Go back to page 1 and sit there and load the whole web again and get the next page you land on. So you're exponentially faster, but it takes you an exponential amount of time to load the web over and over and over to get an answer. This isn't going to do you any good. The problem is we're asking the wrong question. We have to ask a question that works well in the paradigm we set up. So someone, Harrow, Hasidim, and Lloyd, came up with an algorithm that solves AX equals B, general linear equation solver, exponentially fast. Beautiful. But when you ask for the model back, you're back in the same PageRank problem of you get samples of little bits of the model, and now it takes you forever to get it back, and it's useless. But ask a different question. Solve the model, and then ask the model a question that has a very low bandwidth output. So for example, you model a radar sending a signal out into free space. There's a stealth fighter out there, and you want to know the radar cross-section. Well, modeling it is a linear algebra, a simultaneous linear equation problem. You do the fluid dynamics, you solve the problem, but you don't ask for that. Now you say, I'm going to ping it with the radar. Please tell me what the cross-section is. That's one number. You're done. And now you're exponentially faster than any classical technique that could do it. So you can do this if you can get the right circuits. It turns out everyone always leaves out some of the details of how you really get this done. So we're doing the research on that piece. But we have implemented it in Liquid. And this is ongoing research to make this into a full general solution. There is a booth here by DWave. There are a number of people here who either own DWaves or are part of DWave. I'm not giving a talk on DWave today, but I do want to say that the Hamiltonian to the upper right, that is the DWave Hamiltonian, you can simulate in liquid. And you can sit there and do a lot of their published examples on small numbers of qubits. We do have 2 papers we've written. We did over 1 million runs on DWave machines and did over 1 million CPU hours of simulations in our research clusters. And the bottom line is the first paper says, yes, it is quantum. They are qubits. You get entanglement. It is quantum. The second says, it doesn't scale. Now, that's not a problem for me. This is very early on, and this is a machine that lets you actually play with qubits, lets you actually do laboratory work, lets you do analysis, and I'm very happy that that machine is there and exists. But no, I don't believe you're going to solve, real-world hard problems on this machine. It's not time yet. We've got a long way to go. The second paper, by the way, was picked up by Science, and so you can find it there if you're interested. So now let's switch to an area I'm actually very happy with, which is quantum chemistry. Again, the equation you're simulating is the upper right. That's the 1 and 2 body terms. If you're in the materials talks this morning, you saw this Hamiltonian a couple of times show up. What's interesting is the axis on the bottom, the x-axis for the spatial basis functions, that's the number of qubits you need. So you'll notice something even as complicated as cholesterol can be way down below 600, 400 qubits, and there are other ways to make this even smaller. So you don't need a heck of a lot of qubits to do this. Liquid, we've been able to simulate all of these. I can go up to, like I said, on the order of 30 qubits. That's enough to do all of these molecules and see how well they work. And we've written 4 papers over the last year on the problem. And the problem is no one's ever costed out how well does a quantum computer solve quantum chemistry problems. We know we can do it, but how good is it really? And what we did is we took a look at a molecule called ferredoxin, which was the IARPA challenge. The reason it's interesting is iron has d orbitals. As soon as you get to that row and lower in the periodic table, you can't solve them. This is back to those supercomputer usage for quantum chemistry and quantum materials I showed at the beginning, that these are just not doable. In fact, it's intractable, period, lifetime of the universe. So then we plugged in the numbers what everyone was assuming for a quantum computer. And it was 24 billion years to get one answer out. I can't sell quantum computing on that, but that's really where accepted scaling was. The first paper, we said, okay, there are a lot of things people are assuming wrong, and we look at it carefully. You'll see that it's more like 850,000 years. Well, it's a little better. I mean, I'm not going to be around for that, but it was better. In the second paper, we got it down to 30 years. Now that's now in human scale. That's good, but still we're not going to wait around for deep thought to give us answers. And it's something that all of the changes to that point were structural changes. We found parallelism, circuit simplifications, reductions, things we could do. Then we hit the third paper and got it down to 5 days. And then there's the fourth paper, we got it down to an hour. What was magic here? Why did this happen? Well, if we take a look at the molecules, the very top blue line are the various molecules we were simulating, and that's the accepted scaling before we started. The first 2 below that, the orange and the white, are papers 1 and 2. But while this is going on, up to 30 qubits, I can simulate with liquid. So I went and simulated. And I don't get those results. I'm getting something way, way, way lower. It turns out the error bounds were too loose. No one had ever pushed the theorists to say, yeah, but these aren't random Hamiltonians. These are things nature has created. There's symmetries, there's efficiencies, there are all sorts of things that make the problem easier than you'd expect. They're not as hard as could possibly be. And we started going through and analyzing, and by the time we hit the third and the fourth paper, we're right down in the scaling I was seeing. So here's an example where simulation informed theory, and they went back and took a look at the theory and found out what they could do to the theory, and now we have both in very good agreement, and we have an idea where things go. I also want to mention we have another paper in progress at the moment working on nitrogenase. Remember I mentioned fertilizer at the beginning. This is the molecule. Notice it's got a bunch of irons and a molybdenum in it. Can't do this on a classical machine. So we're working with quantum chemists to figure out how we would simulate this on a quantum computer and how long would it really take, how hard it would be to get the answer to a real problem, not just a challenge problem that somebody came up with. So that paper, when that comes out, is all about, okay, here's what we think it'll take for a quantum computer, first generation of, that would be able to solve a problem this hard that we really need solved. I'm not going to spend any time on materials, mainly because we just don't have time. There's a whole separate talk on materials. I just want to mention that the Hubbard model is a model we've done. We have a paper out on this using liquid that lets us model high-temperature superconductivity, how much doping yields the likelihood of superconductivity, this type of thing. The Anderson impurity model via dynamical mean field theory is a technique that will let us do very complex materials. And the nice thing about materials, why I really like it even more than chemistry, it scales linearly on a quantum computer. Adding sites really costs you per site, as opposed to adding molecules, things go up as this end of the fourth scaling. It's much harder to do. But the Anderson model will let us do things like Mott insulators, condo physics, quantum dots, all sorts of interesting things we make all sorts of things out of that we can't simulate any other way. And we have another paper we've just done on variational eigensolvers. This is really kind of interesting. This will let you do quantum chemistry and quantum materials on physical qubits, very few qubits. I can do water with 14 qubits. I can do a couple of plaquettes of Hubbard, say, with 16 qubits. That's nothing. Unfortunately, it's not efficient. This is, not how well my dog talks, it's my dog talks at all. This would allow us to compile a quantum circuit onto hardware that's no more than about a year away and actually solve the problem. These aren't problems you couldn't solve on your laptop a heck of a lot faster than I can do on the quantum machine. But this would show that the quantum machine can solve it, and that's the first step. We've got to crawl first. So the variational eigensolver looks really interesting for within a year or two, we might start seeing experiments doing this. I do want to mention one thing about the DMFT. As I said, it's a whole separate talk, but this also tells you how I think quantum computers are going to be used. So we start on the classical side, we make a model. We have a material we're interested, we have some ideas, and we have a model that we're going to build. We take that model, we throw it on the quantum computer. Once it's on the quantum computer, we can efficiently solve how well that model works. We're not going to tweak it, we're not going to change it, we're just going to find out how well it works. We're going to get the answers back, low bandwidth, so it's easy to do. And then we're going to use the feedback to do a self-consistency model to update the model and rinse and repeat. This is a machine learning loop. And what you've done here is you've keep refining a classically defined model. So at the end, you're not asking the quantum computer for the model back, you're just asking, is this better or worse? And you're finding a search space to pick the model. But when you're done, you have something that's efficiently loadable on the quantum computer to ask questions of. What's the ground state? What are the catalytic rates? What's the diffusion? What, ... So this, to me, it looks very much like you'd use a GPU. This is how you would use at least the first few generations, as far as I'm concerned, of quantum computers, is as a coprocessor that's really intelligent about this. I'm running out of time, so I'm just going to mention Solid. The whole point of Solid is to be able to compile these algorithms instead of for simulation into real lab hardware. It understands the various temperatures in this fridge that's on the right. It understands the various technologies you might have. There was a question in the Beyond Moore's Law session about superconducting logic. You might have that down at 4K. You might have A to Ds and switches down at 20 millikelvin. You probably have normal CMOS at 77, and then room temperature. And this system knows how to compile among all of them, various technologies. You actually, as a user, can plug in target platforms and machine models. And this is a system we're building to actually work with the first generation just of lab equipment, and then down into actual quantum computers when we have them available. Again, I'm going to go through this just really fast, but you have a high-level language that's mixed classical and quantum. It's not pure quantum anymore. It understands both. You get an abstract syntax tree back that we thank the compiler for, and then we throw the rest of the compiler away, and we have our own compilers after that. We do symbolic execution of the code with greedy evaluation to try to get as much of it put away as possible. We retarget, and we finally execute it either as circuit simulation, hardware control, or rendering if you just want to draw what you have. The language is still Fsharp. It's embedded in it. You have unitary operations. You can add controls. The big difference here is when I have something like a quantum Fourier transform, that's the entire code for the QFT. The quantum stuff is in yellow. When I say adjoint, I say invert it. It doesn't invert a circuit. It takes that code, flips it backwards, runs the loops backwards, finds the quantum operations, and inverts the gates, however deep that may go, maybe millions of gates, and you get back out something just as tight that now is the inverse quantum Fourier transform. So the point is this system really understands both the classical and the quantum and knows how to compile, optimize, manipulate them very efficiently. Okay, so this is back to that website. This is how you get Liquid. There's a GitHub site with extensive instructions on how to install and run it, full documentation, 100-page user's manual, 500-plus pages of API docs, samples covering almost everything you've heard today, maybe even a little bit more, teleport Shor, quantum chemistry, quantum error correction. There's a video tutorial that walks you through the whole process of writing code with it. There's community feedback and sharing. It's a GitHub site. People are welcome to contribute and pass code back and forth among each other. On the site, it asks you to sign up for the listserv. I would ask that you do that, mainly because that's how I justify the project. If you've signed up, that tells people you actively were interested, you just didn't go to the website, and that's how I get headcount and I get people to work on this. And finally, I mentioned that if you go to archive.org and look for my name, Wecker_D, you'll get all the papers we've written using Liquid and the research we've been doing in all these areas. Thank you very much.
Thank you, Dave. So we have time for a couple of questions. I've already received some of them. Maybe one, Dave, you already touched it in your presentation. So there was this slide on DWave. Mm-hmm. Can you elaborate a little bit on the type of qubits they're using?
Well, the qubits are flux-based qubits. Mm. They're semiconductor. They're made with a standard semiconductor process. They use Josephson junctions. So when people asked about RQL and asked about the logic in the post-Moore's law session, a lot of that logic is used in it. The problem is the qubits are very short-lived. So you have a lot of qubits. They have small connectivity. There's this four bipartite graph called a chimera graph, and then they connect across. So you have to connect far to get to places, but by the time you jump very far, you lose coherence. So you can show it's quantum, you can do certain things with it, but it is something that is not a general purpose quantum computer.
Okay, thank you. Then I have another question. So you mentioned solving iron and solving water. What does this actually mean? So which type of questions about water and iron do you want to answer?
So there are all sorts of observables, things you can find out about molecules or about materials. In the case here, when I say solve, we're going for the ground state energy. It's the easiest observable to actually know you got it right. It's of interest in general. And so the examples I'm doing are all of the ground state, but you can do other observables.
Okay, so yeah, maybe I have also another question. So how do you believe, it's a little bit of a question about your vision. Mm-hmm. So how do you believe will people in the future interact with quantum computers? So will they have accelerators, wireless-enabled accelerators sitting in their refrigerator, or will there be a quantum cloud? Quantum cloud.
At least of the technologies I'm talking about, you got to be at 20 millikelvin. You're 100 times colder than outer space. So this is something that easily sits in a data center. That's not a problem. You also need a lot of classical computing to both run and use the quantum computer. So you're going to want the supercomputers next door or even integrated with the quantum computer. So this is very much a cloud-type environment.
Okay. Do we have further questions, either through the SC15 app or by using the microphone? Okay, there's a question.
When you were estimating finding, or the time it takes to find a ground state in the various molecules, mm-hmm. You showed the line of Liquid being able to solve up to 30 qubits. How did you estimate the time it would take to solve that particular molecule without the use of a quantum computer? Were you just estimating gate times and number of operations, or?
Yeah.
I'm not sure how you came up with that number.
Yeah, in general, the problem is more one of when we get to the DNF orbitals, there aren't any good classical techniques to get the accuracy level we're talking about. So it's kind of hard to put, that's why it's lifetime of the universe, because it gets down to the point of we have no way of knowing how to do that. Organic molecules we do really well. We do them on supercomputers all the time. We know how long it takes. We know what they take to do. And whether or not quantum will ever beat them at the higher levels of the periodic table, I'm not so sure. Okay, we probably could get to parity, maybe, but you've got more flexibility on the classical side. There's things you can do, classical programming that I just can never do on a quantum machine. So as far as the extrapolations, though, we've looked at how the errors go with the complexity of the number of gates. We know the gate count for, say, ferredoxin or for nitrogenase. We know exactly how many gates it will take. We know what the error levels look like given the error scaling. So we know how many times we have to execute to get the error down. And so given all of that, we get a pretty good extrapolation. And of the molecules we can hit, the extrapolation fits perfectly once we've made this formula. So we have a good feeling about it, but can I guarantee? No. The fourth paper, for example, depends on the heaviest atom that's in the molecule. And we have no idea if it's really one heavy atom or multiples or combinations for the formula because we can't simulate that. It's too big. So there are a couple of places we have to say this is our best estimate. And we also give worst case, if we're wrong, how bad it can be, and then where we think it probably will hit. And the papers go into great detail on that.
Okay. Dave, one last question. So how long do you believe will it take until we can use quantum computing to solve the problems that we were discussing?
I already got into trouble once last month. The press picked up a quote from one of our papers in the abstract. They never read the rest of the paper. They just read the first line that says, quantum computers in 10 years. No, that's not what the rest of the paper says. Let me give an example. Ozone. We want to model ozone. Ozone is only about 34 qubits is needed to do ozone. That's only been doable on a supercomputer. And again, this is lighter atoms, but on a supercomputer as of 3 years ago. So that's almost state of the art, 30 some odd qubits. As Matthias was saying earlier, we're about a dozen qubits now. My guess is we'll be at the 30 range in the next 5 to 10 years. I would say 15 to 20 is my estimate to do the big, beginnings of the first really interesting, impossible to do problems today. And so that would be my personal estimate, but take that for what it's worth.
Okay, then thank you again for this very insightful talk.
Pleasure.